So let me start with a blank slide here. What we have learned yesterday, that now the how does the if you're talking about hydrogen atom, you have in one, so 1s orbital is here, then n is equal to 2, 2s, 2p would be here, or we say that they are degenerate if, and then 3, 1, 2, 3. So इस तरह से आपको 3s, 3p, 3d. This is the situation in hydrogen atom. In hydrogen atom, this is what we have, and this thing undergoes a change when in a multi-electronic system. Multi-electron system, what changes occurs? You have these energy levels will show up like that. So 1s remains here, मतलब almost just एक simplification है diagram का, ये ऐसे ही रहेगा. 2s will change, you will have, so let me have a dotted line over here for sure. So this is now my 2s, 2p. In a multi-electronic system, this is what has happened, and oops, क्यों ऐसा हो रहा है? इसको नहीं मिटा पा रहे. So we have 3s, 3p, 3d. So this is there is staggering of energy levels. So just like 3s, 3p, 3d were having same energy in case of hydrogen atom, but now they are different. Why they are different? What is the reason why it has changed? It is the interaction of electrons with electrons, inner core electrons with outer electrons, and this interaction changes the whole thing. It gives rise to shielding and penetration, and because of this shielding and penetration, the energy levels are getting split, they are getting staggered. You have, so if I, yeah, so this is how things happening, and this is what we saw here. And yeah, when you have 4s, और अगर आप यहाँ पे fourth वाला दिखाते हैं, तो let me put it like n is equal to 4, s, p, d, f, 4s, 4p, 4d, 4f. तो ऐसे करके यहाँ पे आपका 4s वाला 4s आएगा, और ऐसे स्क्रीन के बाहर फिर बाकी सब चला जाएगा, अभी मैं दिखा नहीं सकता. So that's how hydrogen atom versus. So what is the reason? So in between, what has happened? We have changed. So this the color, this thing, what has happened here is that there is staggering of energy levels, and this has happened due to the shielding and penetration. These two things had come into picture, and we had, and this thing is changing the whole thing, and because of this, So because of this, you have entire splitting of the energy levels with respect to the L values in accordance to the N value. And now you also understand that 2s and 2p, when you are comparing, 2s has larger radius, I mean most probable radius, smaller radius. Similarly, 3s larger radius when you are looking at 3p, smaller, 3d smallest in, if you are comparing the three, but the energy is reverse, and that lowering of energy is because of the penetration. एक और चीज मैं आपको बताना चाहता हूँ. Whenever we talk about penetration, we treat that orbital as the outermost a part of the outermost shell. तो बाहर वाला अंदर वाले जो शेल्स है उसके अंदर वो इलेक्ट्रॉन चला जा रहा है, उसी वही पेनिट्रेशन है. इट इज cutting through the layers, it is penetrating through the layers of electrons, inner core electrons, first shell, second shell, और तब वो न्यूक्लियस के पास पहुंच जा रहा है, सेकंड शेल. तो सो थर्ड, सो वी आर ट्रीटिंग, अगर आउटर इलेक्ट्रॉन की तरह ट्रीट करेंगे किसी को, तब पेनिट्रेशन की बात करते हैं. और जब वही ऑर्बिटल किसी बाहर वाले के लिए शील्ड का काम कर रहा है तो शील्डिंग की बात करते हैं. So when we are talking about shielding, it is a property of inner core orbitals, inner core electrons. Two things you must understand, otherwise you will be always confused. ध्यान दीजिएगा. ऑफलाइन क्लास में कल एक बार डिस्कस कर लेंगे, वो भी आपको समझ में आ जाएगा. ठीक. और हाँ, so this is what happens. And now we are at the last part. Last part in the sense, not of course we have a very big, we will discuss at length the spectroscopic transition in multi-electronic systems. But before that, let's try to understand what, as I said, कोई भी रूल जो आप रटा करते थे, सबके पीछे एक बहुत थॉट दिया गया है, बहुत सारा डिस्कशन हुआ है, एंड देन वो एक लाइन में, एक सेंटेंस में समराइज कर दिया गया. उस समरी ऑफ अ जनरल ट्रेंड इज यू से इट एज अ रूल. ठीक है. तो वो समझना जरूरी है कि क्या है, हाउ इट हैज कम अबाउट. सो हुंड्स रूल रटा हुआ है आप लोगों ने, बट व्हाई? सो यू से जस्ट हाफ फील्ड है, हाँ ये स्टेबल होगा, स्टेबल होगा, लेकिन क्यों स्टेबल होगा हाफ फील्ड वाला, इसको कभी आपने सोचा ही नहीं. ठीक है ना. बस Hund's rule इज नॉट द एक्सप्लेनेशन, इट जस्ट अ जनरलाइजेशन ऑफ अ ट्रेंड. ओके. उसी तरह से सिलेक्शन रूल को भी आप रीड करते हैं, ये क्यों हो गया था, हाँ हाँ सिलेक्शन रूल, सिलेक्शन रूल नहीं, आप बोलिए कि कंजर्वेशन ऑफ मोमेंटम या कंजर्वेशन, और यू आर ट्राइंग टू डेवलप द डाइपोल, ट्रांजिशन डाइपोल बन रहा है, नहीं बन रहा है. इस तरह से आपको एक मेच्योर साइंस स्टूडेंट की तरह बिहेव करना है. डोंट राइट very superficial answers, right? सिलेक्शन रूल है इसलिए ये सही है, ये हुंड्स रूल है इसलिए ये सही है. नहीं, you have to go into the depth of that, why it is like that. Reason is not the rule. रूल तो बस बोल दिया गया है. ओके. सो मैक्सिमम नंबर ऑफ पैरेलल स्पिन्स जो इसमें आपने पढ़ा है. सो ओके, वी हैव हाफ एन आवर. So what happens is that, let me go to this picture. Now when you are placing two electrons in the same orbital, what is the situation? Of course there will be repulsion that we expect, and due to and there will be a tendency to minimize that repulsion, क्योंकि repulsion होगा तो energy बढ़ जाएगी system की. So if we have to reduce, what is the possibility, what can it do? Let's take example of let me where is that. So this is what tends to happen when you have one electron, it is like this, two electrons, it is like two parallel space. So why this happens? Three electrons, it will be like this, and so on. But why it is happening in this manner? And we say that multiplicity, you already know what is multiplicity, multiple spin, how many spin, so that maximum total spin possible, or the maximum number of parallel spins that you express as a number of unpaired electrons plus 1. So let's try to understand the reason behind that. So let's understand two things. Whenever you have electrons occupying the same region around, so in one area around the nucleus, you are trying to put two electrons together. So they will have repulsion amongst themselves. You must overcome that forces of repulsion. So this is, so you have to do some work, you have to give some energy to the system. So that thing is what we represent as Coulomb energy of repulsion. Pi, this is capital Pi with subscript C per pair of electrons. So this is what you must overcome. This is a repulsion that you must overcome. Okay, so there will be a natural tendency to minimize the repulsion. क्यों बेकार में सिस्टम की एनर्जी बढ़ जाएगी? तो if there is possibility, if there are degenerate orbitals available, then it will try to go into a different area around the nucleus. So let me, कहाँ गया वो picture? हाँ, there will be additional thing that we will let me just go to the slide. हाँ, just here. Consider this thing. So let's talk about the configuration when there are two electrons in p. If we have two electrons in the p orbitals, and let me just take you this. Oh, okay, so can you visualize this situation that we have here? 1, 2, and 3. Three possibilities we are discussing. What happens to the energy when, so there initially we start with 3 degenerate orbitals and then start arranging the electrons. We find that when we are putting, so we have px, py, let's say pz orbital, px, py, pz, like that. Okay, so let's for the moment consider two orbitals, px, py, pz. Let's draw three pictures. Okay, so here we go. This is so at, what is this? This is my nucleus. At the center of this, हमेशा ऑर्बिटल ड्रॉ करें तो न्यूक्लियस को जरूर दिखाएं. Okay, so just एक मिनट sorry, let me do this very. So this is my p. So we have two orbitals. This is my py and this is my px. Same thing, I can think of this part, and let me just okay, so let me just okay, फिर से ड्रॉ करना पड़ेगा. ओके, नहीं पहले मैं ऐसे कर लेता हूँ. So in a similar fashion I can draw it here. So अपनी कॉपी में भी ड्रॉ करते जाएं. पेन और पेपर लेके बैठा करें, सिनेमा की तरह ना देखें मेरी क्लास को. ओके, क्लास को क्लास की तरह देखें. ठीक है. So this is again this is a rough sketch again. So this is for px and this is again I can draw another set of things are here. सो फ्री हैंड ड्राइंग कर रहा हूँ, थोड़ा सा गड़बड़ हो सकता है. जस्ट ट्राइंग टू, एक मिनट, सॉरी, थोड़ा सा प्लेसमेंट स्लिप कर जा रहा है. ओके, आई यू ट्राइंग टू, okay, so let me try to distinguish. So we are having px orbitals and we have py orbitals, and the three things can be visualized. So first thing is that try to visualize what these pictures electronic arrangement says. जो तीन arrangement है 3-dimensional space में, जब उसको हम visualize करते हैं तो कैसा होगा. So that thing py, py, py. So now what you have, px, you have electrons which is upspin, py downspin, px upspin. sorry, इस केस में मैंने क्या किया. So 2 electrons together here and 2 electrons one over here in the py. ठीक है. और इस केस में px दो पैरेलल. So अब तीन situations है. So in the first case, what is here? So we are having three situations. 2 and 3. So what is happening here? Number one, what you see here, electrons. So this is at the center. Remember, at the center you have nucleus. Nucleus is positively charged, right? This is your nucleus, positively charged, right? This is your nucleus. Don't forget that. This is your nucleus, and that is the arrow that we have shown is the electron, right? Nucleus with a positive charge. Now think, you have electrons, nucleus at the nucleus. So just a moment, 2 electrons occupy same region of space around the nucleus. In this case there will be repulsion, and so the energy of this will be high, right? Okay, same nucleus. So this will give out this, there will be repulsion. So this is leading to high energy. So energy of the system will increase. Okay, that's one thing. In the second case you have overcome it. 2 electrons now with the same upspin and downspin, px and py. Now you have, they occupy two different regions of space, so repulsion is less. 2 electrons occupy different region of space around the nucleus, repulsion is less. ठीक है. 2 electrons occupy different space around nucleus. So visualize, try to understand. Your nucleus is positively charged, the electrons are now more spread out, they are occupying different positions around the nucleus, so the repulsion is minimized, repulsion is less, and so this situation will have less energy. The second situation is having less energy as compared to the first situation, right? Around the nucleus, and so less repulsion, and so less energy. Energy is reduced. In the third situation, they are still around different occupying different region of space, px py. So तीन अलग अलग एरिया, दो अलग एरिया में हैं electrons. And there's additional thing that happens here. It has been observed that when the energy, they have same spin, same energy, the two electrons can now exchange places, and that gives rise to exchange energy, which is energy is further released. So this situation arises when the two electrons in px and py orbitals, or any two degenerate orbitals, have same spin. Then there is exchange of places, which can further give out release. This is a purely quantum mechanical phenomena occurring in this kind of systems. And two electrons have same spin, दो different areas में हैं, repulsion तो minimize कर ही दिया. In addition to that, they have same spin, same energy. Initially जो हम same energy के orbitals में हैं, and then so this is, they can exchange their places. The two electrons exchange places, exchange happens. So two electrons can exchange their places, and this is energy decreases further. So this is called exchange energy. The energy released when two electrons are occupying two degenerate set of orbitals, and they have same energy, same spin. Then due to the mutual exchange, there is some energy released, which is called exchange energy. Energy released. So this decrease in energy is exchange energy. So we say that exchange energy is a negative term, and this happens typically in this kind of system whenever you have situation. So if you have to say energy in terms of energy, this is high. In terms of energy, the situation is, this one is 1 is highest energy, 2 and 3 is the lowest, much less in the third case. So 1 2 3 situations that we have encountered, the order of energy is something like this. Okay, because the exchange energy, because of the exchange of places that happens between the two electrons, we have the energy decreases, and that thing is what we know as exchange energy. And this exchange energy lowers the energy further. So lowering of energy happens when you have this kind of situations. So let's just okay, so this is what we have seen here is that first configuration involves Coulombic energy. So there is repulsion, they are occupying same region of space around the nucleus, so they are, the attraction of nucleus is not that dominant. It is the repulsion is, there is greater repulsion. So electron repulsion is accounted for. We use this symbol pi c to represent this repulsion between two electrons when they are placed between in the same orbital. Okay, so energy of this system is higher than the other two by a factor which is represented by pi c. We are trying to be have some mathematical thing here. In the first two, okay, so I have already discussed all the three diagrams with you. So plus or minus spin, so two possible ways we have arranged. 2 1 1 2, like this. So this is the what, so this is the, when we have parallel spins, we can arrange this thing. Either electron number 1 can go to this orbital px py, so that we have discussed just now through pictures. So this is what is showing the exchange. So two electrons in px and py orbitals, and both the labels have changed. That one is going in the place of 2, 2 is going in place of 1. So that is, so px py, you can see it has exchanged the place. Now number 2, electron number 2 is, so this is what we say is the exchange energy, pi e, capital pi with a subscript e. So this is a negative term. As I said, there's release of energy because of this kind of arrangement. Further lowering of energy is observed, and this is given a negative sign. The pi c that you have seen, the Coulombic energy that was repulsive, this is a positive term. So this is a positive term. Okay, increase in energy causing, and this one is negative. Okay, so this is the reason. Actually, you will find that when you have half filled or subshell, that is giving you a very very low energy. Maximum number of exchanges possible in, as compared to any other its neighboring arrangements, like so that's a thing. So higher the number of exchange possible, lower is the energy. So because exchange energy will, in magnitude, the exchange energy will increase. Exchange energy is a negative term, energy is released, so overall the energy of the system will go down, lowering of energy will happen. So the third configuration that we saw with two parallel electrons is the best one. So the one exchange of energy that we have seen over here, it leads to lowering of energy, and that exchange, so see here the exchange has happened. And now if we try to put it as energy level diagram, then this is what we have. The situation for 1, the situation 2, this was the thing, and situation 3, when you were putting both the electrons in same px orbital, px py, py and px py with parallel spins. So, and what you are seeing here, this is the Coulombic. Between this and this, the difference is that of repulsion. Here the two electrons occupy the same orbital, that is same area around the nucleus, and so there is repulsion, and that repulsion is given by pi c. And then when you are separated them with the same, keeping the spin same, unchanged, then this is the situation number 2. And when you finally make both the spin parallel, in that case there is additional thing, that is exchange energy, and that is the difference of energy. So this is the lowest, so this one is lowest in terms of lowest energy because of interaction, exchange interactions. Repulsive interactions, it has, in this case this was highest energy. So three possibilities, we have considered three possibilities how a P2, when we have P2 configuration, how the electrons can be arranged, and we found the one with the lowest energy when the electrons are having parallel spins, and greater is the number of parallel spins, greater is the exchange energy. I am talking about the magnitude of exchange energy that we are talking about. So it is energy, so greater amount of energy is released, and this is actually, you will find out, is the reason for spatial stability of these half filled or fully filled subshells. So when we say that we are trying to maximize the number of parallel spins, when we are trying to have higher multiplicities, this is what it means. Okay, and so what we write here, that starting from situation number 3 to situation number 1, total change in energy is pi, capital pi, and it is a sum of pi c plus pi e, the exchange energy and the Coulombic energy. Okay, so it is a capital pi from the Greek alphabet. Small pi आप जैसे लिखते हैं वैसे capital pi लिख सकते हैं. So this is the how we represent it. Total pairing energy, capital pi. ध्यान दीजिएगा, this is what we have been also been using in first semester while discussing d orbitals, right? वहाँ पे भी capital pi लिखा हुआ था, आपने ध्यान नहीं दिया होगा, मेरे slides में रहा होगा उस टाइम. Okay, so if you pay attention to this, so whenever we talk about pairing of two electrons in a one orbital, it necessarily involves two things: the Coulombic energy, what we have seen here, repulsion, overcoming the repulsion, and also if you are putting it earlier, there was possibility of two degenerate orbitals, then it also involves exchange energy that is coming into picture. The Coulombic term is positive, pi e is negative, so greater is the pi e, the energy lowers down. So for any two electrons, the energy exchange energy is same, so you can treat it to be constant. You can treat pi e to be constant for electrons with the same spin, exchange of electrons with the same spin, and then you can calculate the total exchange energy. N is the number of electrons with parallel spins, and pi is the number electron exchange energy released per exchange. Any pair of two electrons with parallel spins in two different degenerate orbitals, this is the thing. So this is how you can calculate the exchange energy. Summation of n minus n. What is n? N is the number of unpaired parallel spins. Parallel spins. Number of electrons with parallel spins, right? So it is a very simple thing. Without going into the formula also, you should be able to draw the different exchanges that is possible. So when we talk about so this is what was summarized in a sentence, and that's what's called as Hund's rule. So when they have orbitals are degenerate, unpaired configuration over the paired configuration, so we have always this unpaired. If you have degenerate set of orbitals and you have to put 2 or 3 electrons in them, you first tend to have unpaired configuration that will have lower energy, because Coulombic energy is you are not have that problem of overcoming this Coulombic energy अगर आप अलग अलग रख रहे हैं. And total pairing energy we have seen, it is sum of the Coulombic energy plus the exchange energy. So the final configuration we have just seen. So P2 configuration में भी आपने देखा 3 different energy हो सकती है overall system की, how the system energy can change. So that is what we have to keep in mind every time we are having a multi-electronic system, degenerate orbitals and the same spin. So same energy, same spin. अगर degenerate orbitals में electron को रखना है, if this possibility is arising that they are initially from the orbital point of view they are having same energy, same spin, then the exchange of places can happen, which leads to release of energy, which is called exchange energy. So that means so इसी को आप जब आप finally draw करते हैं, you try to see as you move through periodic table and try to fill up the electrons, you will naturally find that this tendency will be there, and one set of electrons is filled. Okay, so first lower energy is filled first, then if you have sometimes this breakdown can happen when energy levels of two different sets are very close to each other, 4s and 3d. This happens, okay, because they are so close in energy that pairing energy is nearly the same as the difference between the levels. So there's a tendency that electron may go to the 4s first and then 3D. So we will have more on this in the offline class tomorrow. We'll try to understand draw. Okay, so we'll practice. So you have to practice more on this calculating the exchange energy for different system D4, D5, D6. We'll discuss that more in the next class. नहीं ये मैं ऑफलाइन में करूँगा अभी के लिए. ओके सो ठीक है. So you just try to calculate the exchange energy for, let's say, compare. Let me tell you, I think compare P2, P3, and P4, and find the number of exchanges possible. So higher the exchange, greater will be the energy. So which one is having? So just we'll discuss this point again. So find which one is having lowest energy. Which one has lowest energy? Explain. So you focus on this. Write an explanation of this P2, P3, P4, and don't write because of Hund's rule this is more stable. No, now you know what you have to do. Explain in terms of exchange energy, pairing energy, that thick. So this is the question you try to answer. We will discuss in next class. Okay, that's all for today. Thank you.